So, Poisson distribution. So, if you're interested in finding out the probability that there are few people, let's say on an average, 200 people are going to buy a product X from a store on a Friday night, then we can also ask ourselves a question that what is the probability that more than 300 people are going to buy? So on an average, we know, and we want to find out more than 100 people are going to buy this, right? So there you can use Poisson distribution. So I'll tell you about the characteristics of the Poisson distribution after telling you few examples of the Poisson distribution. And one, it is a discrete distribution. So the random variable X can take the value 0, 1, 2, 3, and so on. It's not a continuous distribution. So please write example 1. So I'm not solving them, but I'm just giving you example where it could be used, and then we'll write the characteristics of this. So if the average number of people buying a product X from a store on a Friday night is 200. So we know the average. We know the average. And then what is the probability that more than 300 people will buy the product? So that is example 1. Other example could be, for example, so you are running a call center, right? And you are getting a certain number of calls per minute or per hour or whatever. And there are certain calls which require more than 20 minutes to handle, right? So you can calculate the maximum number of calls using Poisson distribution. You can actually calculate the maximum number of calls per hour that might come, which are going to require more than 20 minutes of customer service, right? So calculate the average number of customer service calls per hour that require more than 10 minutes or 20 minutes to handle. Right. So you can calculate using Poisson distribution. What you can calculate is the probability of the maximum number of calls that you might get per hour which are going to require more than 10 minutes of the customer service time. Mm. So we can find the probability of maximum number of calls per hour that might come requiring more than 10 minutes. To handle using Poisson distribution. Using Poisson distribution. So if you look at it carefully, you find that the this experiment, this Poisson distribution experiment, this is requiring few things. You need to have the knowledge of the average number of times the thing is occurring. That is, K is the number of times that the event is going to happen in a specified period. So you need to have that knowledge. And events are occurring independently. So whether it is, I mean, I am buying a product X from a store or you are buying a product X from a store, these are independent events, right? I am calling a customer service or you are calling it, that's an independent event, right? And at a point of time, the two events, event in question cannot occur simultaneously. So what I'm trying to say is that there has to be some difference in time. So when you are buying it or you are calling the customer service and I'm calling the customer service, there should be some time interval between the two, always, right? So, and the number of trials are sufficiently greater. So when you have large number of trials, so let me just write a few things. So K is the number of times an event happened within a specified period. Within a specified periods, and these K are simple numbers 0, 1, 2, 3, 4, and so on. So events occur independently, right? Then there must be some interval of time, howsoever small it is, right, that separate the occurrence of event, right? There must be some interval. that separates occurrences of events, that separate occurrences of event. And the other thing is that the number of trials is sufficiently large enough. The number of trials is sufficiently greater than the number of times the event does occur. So what you're trying to say, you're trying to say this, that for example, you are getting, let's say on an average, 500 calls per hour. And there are few, of course, there are few employees in your customer service call center. But the number of times you are going to get more than 10 minutes call, that is going to be very less. So the trials are very, very huge, but maybe the number of times that you're going to get more than 10 minutes call, maybe there are 5 out of 500 and so on. So that is the point. So K is a random variable and the distribution of K in this case is Poisson distribution. So let me write one more thing. And then I'll do one simple question with you. So many of the books, they write Poisson distribution like this: a Poisson random variable will relatively describe a phenomena if there are few successes over many trials. If there are few successive over many trials, right? And the Poisson distribution is also said to be a limiting case for the binomial distribution when n tends to infinity. That is the number of trials they actually tend to infinity. I'm not proving that. So we are just doing it like this. So let me write the formal definition. Please write, suppose we conduct a Poisson experiment in which the average number of successes within a given region is mu. So I've told you that. So average number of calls per hour you are getting, the average number of customers which are buying your product on Friday night. So you know all that. So that average number, that number is mu. Then the Poisson probability is Ex mu is e to the power mu into mu to the power x upon x factorial, where x is the number of success that is going to result from the experiment. Number of success that results from the experiment. Guys, I again and again tell you, right? You can get the most from these recordings only if you sit with uh, your register, your pen, and you're writing it down. There is no other way. So if you're looking at them for some shortcuts, they are not. Uh, so I should be, I really want to urge you to get in the mode of making notes. Then only you will understand it. So when we were in college, our professors, they always used to say this. And at that time, we have never ever given any, what do you call, heed to what they were saying. But when I am on the other side of the table, I realize that when when I make notes, I understand it better, and then I'm able to teach better somehow. At least I try. I don't know whether I'm able to teach or not, but I try, because the understanding gets better. So you also have to do that way. Hmm. Hmm. And there is nothing in the world which you cannot understand if you give time to it. So if you just want quick fixes here and there, that's not going to work. Hmm. So let's do one simple question. The average number of homes sold by a company is 2 homes per day. So we know the average, and we are trying to find out what is the probability exactly 3 homes will be sold tomorrow. That exactly 3 homes will be sold tomorrow. So you know that this is a Poisson experiment. You are given with the average, right? And you have and the probability of selling it, selling one home is independent of the probability of selling the other home, right? So what you have is this. So x is equal to 3. So let me just write this. Mu is equal to 2. That is the average. Since 2 homes are sold, on average, x equals to 3. That is the likelihood which we want to find out. Likelihood that 3 homes will be sold tomorrow, right? 3 homes will be sold tomorrow. So it's going to be like this: e to the power minus mu, which is e to the power minus 2, mu to the power x, mu to the power x. Mu is what? 2 to the power x upon 3 factorial. So you can just leave your answer till here only, or you can find out actually the value of e to the power minus 2. So, and because e is what? 2.71828 to the power minus 2. And in case if you do find this out, you'll be getting 0.180. So the probability of selling 3 homes tomorrow is 0.180, right? The probability of selling 3 homes tomorrow is what? 0.180. So in the manufacture of glassware, bubbles can occur in a glass. So, and the moment the bubbles are going to occur, it is going to reduce the status of the glass to that of a second. And in 1 in every 1,000 glasses items produced, it has a bubble. So in a batch of 3,000, what is the probability that 6 items will have a status of second, or 6 items will have a bubble? So suppose X is the number of items with a bubble. Right? P is what? 1 in 1,000. So it is 0.01, 0.001. I'm so sorry. 0.001, right? And I have not proved this, but just take it like this. Your average is lambda is n into p, the number of times the experiment is done into the probability. So how many times the experiment is done? 3,000 times. And probability is 0.001. So NP is 3. So probability x equals to 6. It will be what? E to the power minus 3, lambda to the power 6, that is 3 to the power 6 upon 6 factorial. Upon 6 factorial. So you can just calculate this. This is the way you find out the Poisson distribution, right? Chali. Thank you, beta.